Now that we've started our discussion on astronomy and energy that travels through the universe, radiation, the form of waves, we can use that information to help start to understand how the universe came to be. And one of those things we're going to do here is talk about the beginning of the universe, or the Big Bang Theory. We want to know, where did all of the space and stuff come from the universe that we live in? So as always, we have our two essential questions that we start with. First of all, what does the Big Bang Theory state? And then whatever the theory states, we also want to know, how do we know that? Because a theory, remember, is an idea in science that isn't 100% proven, but it's pretty sure because of evidence that we have to support that idea. So we want to know, what are the two key pieces of evidence for Big Bang Theory, and we want to be able to describe not only what is each one, but also how do they support the actual Big Bang Theory. Now, when I ask people in class, a lot of times they give me two things about the Big Bang Theory. One, they tell me it's the beginning of the universe, and two, they tell me it's their favorite TV show. So keep in mind, the Big Bang Theory TV show, while it is important, isn't the focus of our topic today, but we will see how their theme song comes in handy. So for starters, what is the Big Bang Theory? Well, it does tell us about how the universe began, and that it did begin from an enormously hot and very dense state. And the idea is that this item, this singularity, was extremely hot, really high pressure. All the material that we know in the universe today was compact into this teeny tiny little point. And that point we call a singularity. And the idea is that about 13.7 billion years ago, this occurred and started to create the universe. So the Big Bang Theory is that the universe began from an enormously hot and dense state, which we call a singularity, and the universe is right around 14 or so billion years old. Now, the idea is that when this singularity existed, some sort of energy came in and sparked the singularity into expansion. A lot of times we hear Big Bang and think, pew, there's got to be some kind of explosion happening. But that's not so much the case. We want to start using this word more, expansion, rather than explosion. And what we see from that original expansion, space has since then, and continues to for the last 14 billion years, continues to expand with time. So there's the Big Bang Theory, and with the TV show, we can actually think about that first phrase of the theme song. You can always look it up or watch for it on every night. And that first line of the song is the actual Big Bang Theory, right? Our whole universe was in a hot and dense state, and nearly 14 billion years ago, expansion started. That is the Big Bang Theory. So you can always think of that little phrase anytime we go to discuss what is the Big Bang Theory. Okay, now the Big Bang Theory, because it's stating things are expanding, like always, we try to make it as simple as possible. And one of the key things astronomers relate the Big Bang Theory to is actually raisin bread. This big complicated idea pared down to the idea of raisin bread, and this is why. What we see here with the raisin bread is a small loaf of dough before it's cooked, and all the little raisins present in there. They're all pretty close together in the uncooked dough. Well, when we cook bread, it rises over time before we even cook it, and as that dough starts to rise, the raisins still stay intact. They do not change their shape or size. The raisins themselves do not change, but what does change is the space in between. The space between is what is changing, and that is the idea that what astronomers have about the universe. We started out in this singularity, this hot, dense state. Expansion started with that, creating everything. There's our galaxies, and over time it continues to expand. And notice here, it's just the area that's getting bigger. The galaxies itself, they've all stayed the same size. but the space around and in between them is what is really changing. This space there, that is what is changing over time. Okay, so on your notes there you have a picture of the fully cooked bread, just to remind us that it's the space in between all the objects that is increasing. And because all the space from everywhere outward is increasing, what we've noticed is there's not really a set center to the universe. Okay, everything is getting further away from everything else. It's not that there's one point that everything is getting further away from. Everything is getting further away from everything else. So that is the idea of Big Bang Theory. And you've spent some time investigating the two pieces of evidence that make up the Big Bang Theory, how we know that things began, slowly cooled down over time to create the matter that then has created our planets, our galaxies, our solar system, all that stuff. You've done a little investigation about each of the two evidences, so we'll summarize them here. The idea was, like we said at the beginning, the whole universe was extremely hot. To get that singularity to start expanding, we needed a huge amount of energy, right? As it expanded, this heat left behind something. The heat from the original expansion of the Big Bang, running out of room there, left behind a glow that now fills the entire universe. Okay, so Big Bang states we have a hot, dense object, the singularity, which started to expand. In order for it to kickstart, we needed some high-level energy coming in to make the system extremely hot. Once that energy was put out there, it started to cool. And it's had quite a long time to cool, right? 14 billion years. Okay? Now, thinking about what kind of energy would be strong enough to kickstart this expansion, we know we're going to look at the high frequency, high energy end of the spectrum, and it's got to be cooled down gamma energy that initiated the original expansion of the Big Bang. And as we know from this being called CMB, what we have left over are microwaves, okay? And if we kind of rewind back in time, the microwaves we have now, if we were to rewind 14 billion years, would be the strength of gamma. So it tends to make sense. It matches up. The other key here is that we see them anywhere that we look in space. Right? These microwaves are found everywhere, and we heard that with Penzias and Wilson. They accidentally found this data by trying to just get their machine organized, right? Pointing into nothing, they ended up finding microwaves everywhere, and that triggered this piece of evidence. So big picture, what we have here is that the Big Bang started with a huge, immense amount of energy. And that huge, immense amount of energy is still out there cooling down after all this time. After 13.7 billion years. Right? It's been cooling ever since. So it started out with the gamma. Gamma was created, 13.7 billion years of cooling has now lengthened the wave and cooled it down to the level of microwaves. Right? So if I were thinking ahead, if I were to collect this data in another, say, 100 million years or so, as that energy continued to cool, eventually all of the material that we would see in the universe would be radio waves. So this cooling is going to continue, and that energy will still continue to cool over time. Evidence number 2 is Hubble's law. Hubble, of course, being a very well-known astronomer for finding other galaxies outside of the Milky Way, and then studying those galaxies with great detail, finding out that those galaxies have a spectrum, just like we see on stars, and we can actually see that pretty much every galaxy studied is moving away from Earth. And so that fact that he found triggered him to do a little data analysis, and he's noticed that as we get further and further away from Earth, as our distance from Earth increases, what we notice is there's a change in recessional velocity, or speed, that galaxy is moving at. So the further away that we get from Earth, we see that the faster that galaxy is moving away from us. So here is what Hubble's law is. As a galaxy's distance from Earth increases, distance from Earth increases, just like we see on the graph here, as the distance gets larger, the speed that that galaxy is receding at is faster. So the farther the galaxy, the faster it continues to move away from Earth. That is Hubble's law. And so again, what does this have to do with the Big Bang? Well, again, Big Bang theory says everything began in a hot, dense state and then began to expand. So if all these galaxies are moving away, there has to be space for the galaxies to move into, right? We haven't found that the galaxies kind of hit a wall or stop moving at some point. They continue to recede with every piece of data that we collect. So big picture here for evidence number 2, because all data show a red shift. Again, red shift means the wavelengths of the galaxy are getting longer, therefore it tells us the galaxy is moving away. It proves to us that the universe is ever expanding. Right? I've got to have space for those galaxies to move into if they continually move further and further away from Earth. So 2 big pieces of evidence here. Cosmic microwave background, saying that this microwave evidence everywhere is left over from the gamma that initiated the Big Bang, and it's there because that gamma has been cooling for 14 billion years. And evidence number 2, Hubble's law, says, hey, all of my galaxies have red shift. They're moving away from Earth. So yeah, the universe has to be expanding because there's space for the galaxies to expand too. There's no end to the galaxy to the universe where galaxies are bunching up. So finally, you have a little brainstorm there on the right-hand side. What do you think is going to happen to our universe? Will it continue to expand, or do you have other plans in mind? So just give me a quick little yes or no, 1 sentence about what you think is going to be happening. Remember, there's no wrong brainstorm. And then finally, you've got 2 summary questions to answer that are noted on the front there. Remember, this is a summary of our material, so we want to be as detailed and complete as we can, especially when we're talking about the Big Bang evidence.